Okay, so welcome everyone. This is a presentation on Control Valves 101, brought to you by the Controls Standards team. Quick side note, this was originally going to be a combined presentation to talk about control valves and flow meters. I was going to tag team it with Taylor Rush. The control valve content kind of ballooned, so now this will be its own presentation, and then I think Taylor's going to give one on flow meters down the road. Special thanks to Andy Bean and Jeff Urick for some content support. Hoping to stick to 45 minutes here. I'm going to have to move pretty fast, but we do have the recording, and I'll send out a link to the slides when we're done. So on the docket today, we're going to start with the absolute basics. Briefly, what are control valves? We'll talk about the types of parameters when you're specifying a control valve, what kind of things you need to worry about. Different valve types, ball valves, globe valves, butterfly valves. And then we're going to get more into the engineering meat side of control valves. Talk a bit about valve authority and why that's important, flow coefficient and how that relates to valve authority, and we'll close it out with some brief talk on pressure independent control valves. And as a quick side note, if there are any questions, feel free to just butt in, interrupt. I'm not monitoring the chat very well. Kyle, maybe if you can keep an eye out, I'd appreciate it. So what are control valves? So fundamentally, control valves are either going to allow flow, typically water, through a device, or it's going to restrict flow through a device. So most commonly, we see this with hot and chilled water coils. So this picture on the right, this is a, say this is a hot water coil with a three-way control valve and actuator. So if we want more heat through the valve, or excuse me, through the coil side of this, we're going to open that valve and send more water through the coil. But if we want to pull less heat out of that water stream, we're going to close the valve. Same thing on a chilled water coil, exact same setup as that picture right there. If we want more cooling, open the valve to get more chilled water through the coil. If we want less cooling, you start to close the valve. Now with both of these applications, that valve is typically going to be able to open and close to any degree. So it could be 30% open, 60% open, whatever you want. One application where that's a little different is with a water source heat pump, where if our heat pump's running, we're going to full open that valve and get all of the water flow into that heat pump. If the heat pump's not running, we're going to close that valve and get no flow. And so further on, we're going to talk a bit more about modulating versus two-position valves and how it relates to these different types of applications. So when we're talking about specifying a control valve, there are a number of things we need to keep in mind. What do we want that control valve to have, and how do we want it to behave? So first up, we're going to talk about two-way versus three-way control valves. So anytime you have a constant volume pump system where you're moving the same amount of water through your loop, no matter what, you're going to see what are called three-way control valves. So on the right side there, that's a three-way valve. You can tell because it has 3 points of connection. That big orange thing on top is your actuator. That's the classic Belimo orange that we see in the field all the time. And so that's the motor that's going to open and close that valve. So with the three-way valve, some of the water is going to go through the coil side if we want to get that heat transfer. And some of the water is just going to get bypassed directly from the supply side to the return side and not go through the coil. And what this allows is for modulating of your heating and your cooling output, because what you the way you want to control your heat transfer is by changing the flow through the coil side. And so by modulating that flow through the coil, it can change how much heat transfer you're going to get, but your total flow is always going to be constant. So if we have 50 gallons per minute coming in on the supply side, we're going to have 50 GPM coming out. But through the coil itself, it's going to be anywhere from 0 to 50. So that is a variable amount. And then this bypass flow is going to be your 50 GPM minus whatever your coil flow is. But ultimately your total water flow, that 50 GPM going to that unit, is going to be constant under all conditions. So looking at a hot water system schematic, one hot water system with a bunch of heating coils. We have our boilers on the left here with their primary circulation pumps. We have our secondary pumps that are going to move the hot water through the system. And then let's say each of our 4 coils here, these are 50 GPM coils, and these are all 3-way control valves, meaning that 50 GPM is constant all the time. And so our secondary pump or pumps, they're going to be moving 200 GPM all the time. Doesn't matter what's going on with the valves. It's 50 GPM at every coil, 200 GPM constant flow. And so this is kind of a classic constant volume system. And for this to work, it really has to have all 3-way valves out in the system. We don't see this a lot anymore, which I'm going to touch base on here in a few slides. So converse to a 3-way valve, you could have a 2-way valve. And so 2-way valves are going to be used anytime you have a variable volume pump system, where you want to vary the amount of water moving through that system. So a 2-way valve also allows for that modulating control, but it's varying the total flow directly with that load. And the way they do that is we take out that bypass. So a 3-way valve has that bypass leg connecting the 2 lines. A 2-way valve does not have that. So it's only got 2 pipe connections, hence the term 2-way valve. And so if you have 50 GPM, or rather 0 to 50, so now it's a variable flow, you're going to have the same amount of flow through the coil, and then out the back end, it's still going to be 0 to 50. So back to our schematic. So same schematic as before, the only difference is we've now replaced all of our 3-way valves with 2-way valves. And so each of our coils are now 0 to 50 GPM. So now we have this variable flow scenario. We now have to control these pumps with variable frequency drives based on the pressure in the pipe system. That's a presentation for another day. But ultimately, these pumps are supposed to speed up and speed down depending on what's going on with the coil needs out in the system. And so if you have 4 coils with variable flow 0 to 50, your total pump flow is going to be anywhere from 0 to 200. Now the problem here is if all of these valves close off, well, now we have a problem, because this pump or pumps are going to deadhead. Those pumps are going to try to move water when it's got nowhere to go. So generally, putting 2-way valves all over the system is not a good idea, because when you get into that low load scenario or no load scenario and those pumps try to run, that water's got nowhere to go. The most common way to fix this, so that valve at the very end, what if we replace that with a 3-way valve? So we change this 2-way down here to a 3-way. Now this coil at the end has a constant 50 GPM flow, and now our pumps are always going to have that 50 GPM minimum. So even if every other 2-way valve's closed, you're always going to have somewhere for that water to go. Now, another way to do this would be to install a dedicated bypass valve somewhere else in the system. A little more controls complexity to that, but ultimately, you have to have somewhere for that water to go in those very, very low load conditions to make sure your pumps are able to operate. So with constant versus variable flow, I mentioned constant pump system. We don't see them a whole lot anymore. Generally, they're not code compliant, meaning the energy code. But if you work in the energy group like I do, I mean, I see constant volume pump systems in existing buildings all the time. If you have a smaller pumping system, you still might see a constant flow system. Generally speaking, the energy code says you got to have variable speed control on pumps that are 7.5 horsepower or greater. Reason being, you can save a lot of energy with your pumps by making it variable speed and controlling that with the variable frequency drive. Reason being, pump power, so kW, and that's really what's driving the energy use of that pump, has a cubic relationship to the pump speed. An important note here, this is idealized condition. So it's not going to be quite as good as what I'm about to show you, but it still saves a lot of energy. So here's that cubic relationship. And so the point at which we design these pumps for, so that's at the 100% pump speed, which is going to correlate to 100% pump power. But you can see a sharp drop off as you slow that pump down. You're going to see substantial power savings. So if we were to drop to 60% flow, which there's probably a lot of hours in the year where you're going to be at 60%, that's only going to correlate to about a 22% power. So that's a big drop. Now, again, those are ideal conditions. Reality is not quite that good, but still, a lot of savings can be made by going to a variable speed pumping system. So we got two-way valves and three-way valves. The next thing you usually have to spec is, how is this valve going to open and close? One option is open and close only. So we call that a two-position valve, or we can modulate the valve. And both two-way and three-way valves can be either of those options, modulating or open close. So with an open close valve, we're either 100% open or 100% closed. So we're never in between those two values. And so to control a valve like that, you need a digital output or DO control point. So the signal you're going to send to that valve, it's either a 0 or a 1. That's it. It's only got two possible positions. And you're going to use this in applications where you either want full flow or no flow, but nothing in between. A common example we see is water source heat pumps. So when the DX refrigeration circuit in that heat pump is going to operate, you want all the water, but when it's not operating, you don't want any of the water. But there wouldn't be a scenario where you'd only want 50% of the water or 60%. Modulating valves, these can be open to any position from 0 to 100%. And so this would require an analog output, which means you can send any signal from 0 to 1 and anywhere in between to open that valve to any open position. And so you're going to use this anytime you need to control flow to varying amounts. Most common example being hot and chilled water coils. So if you only have a 30% heating load, well, just open that valve 30%. You know, don't fully open it. Only get what you need. The next thing to keep in mind is the actuator return. So I mentioned the actuator earlier, the big orange thing. That's our motor. It's going to drive that valve open or closed. But what happens if the actuator fails or if you lose power to the actuator? So there's a few things you can do here. The simplest, you don't do anything. You just fail to what's called last position. So if the valve is open 40% and loses power, it's going to stay at 40%. Or you can spring return it to force that valve to a full open position and get all of the water that could move through that valve. Or the opposite, you spring return to force the valve closed, meaning you're going to get no water flow. And so when you want to do this, really depends on what this valve is serving. So if you have a freeze protection concern, you know, say you're heating a mechanical room that has a bunch of plumbing in it, well, you probably want to spring return that valve open, the heating valve. You know, you're going to overheat the space, but better to overheat it than have all your pipes freeze and burst. But what if you have a chilled water unit serving a server room? You know, needs cooling 24/7. You should probably spring return that cooling valve open. Overcool the space, but that's better than overheating the space. I mean, data centers have crazy amounts of lost revenue anytime their servers go down. But if you had a VAV box with a small hot water heating coil in it, you probably wouldn't provide spring return on that and just fail to last position. And the reason we don't just add spring return everywhere is it does add cost. It also increases your actuator wear and the required torque. That actuator, if it's working against a spring all the time, that's going to wear it out faster. And so ultimately, it's up to the engineer when they want that spring return. Going back to the VAV box application, if you have a large building with 200 VAV boxes, I mean that's a lot of spring return actuators to add for arguably not a lot of value. And then a quick slide here, kind of a special, what I'm calling a special application, which is called a 6-way valve. And if you took a look at this thing and you didn't know what a 6-way valve was, you'd probably be a little intimidated by this big thing you're looking at. But the idea here is you essentially have 2 3-way valves that are stacked on top of each other, controlled off of one actuator. And the idea is the 6-way valve can provide hot water or chilled water to some terminal unit or coil out in your building. Most often we see this with chilled and heated beams. So what's going into this valve? On one side, you have your chilled water supply coming in and your chilled water return coming out. The other side, we have hot water supply and return. And then the black arrows are what we're sending to and from our coil. So if our coil wants chilled water, the valves turn to the chilled water mode and they send chilled water to the coil, or vice versa. Flip to the other side, provide and return hot water. And so this they're using the same actuator. And so on one end of that actuator's action, you're going to have full cooling flow. On the opposite end, you're going to have full heating flow. And then somewhere in the middle, you're going to have neither. I mean, you shouldn't be flowing both at the same time. And this is more economical than providing separate valves and actuator. You can probably save a little bit on piping as well in some of the parts and pieces. Maybe you can cut out a strainer at every unit, for example, save a little cost there. But they do tend to have higher pressure drop, so it's something to watch out for. But a few considerations if you're going to spec a 6-way valve, there are a few things that have to be true about your project. Your heating and cooling coils have to be the same coil. So a standard 4-pipe fan coil usually has separate heating and cooling coils with separate coil connections. That doesn't work here because there's only one set of pipes going to and from the coil itself. Your hot and chilled water chemistry, your propylene glycol percent, namely, has to be identical. So every time this valve changes over from heating to cooling, you're going to have whatever water was in the coil is now going to switch which system it's in. And so if the water chemistry is not the same, over time the water is going to blend. And the freeze protection you thought you had on your chilled water system might not be there down the road if the hot water system doesn't have the same glycol percent. And your application, you have to make sure you're never going to want a simultaneous heating and cooling, which is definitely rare. I mean, generally the energy code says you can't provide simultaneous heating and cooling, but there are those weird applications where you might need that, in which case this isn't going to work. So moving on to control valve types. Probably the most common valve we see is a characterized ball valve. So we usually see ball valves for flow control in smaller pipe, which based on our standard pipe spec is 2-inch and smaller. And if you installed a full port ball valve, which basically means when the valve's open, you can look down the center of it like a tube. We typically use a full port ball valve on like an isolation valve, which would be either open or closed. But with a control valve, we don't generally like to see full port ball valves. Reason being, they don't give a linear relationship to heat transfer. And really what that means is you open the valve just a little bit, you just crack it open, you're actually going to get a lot of heat transfer, even if your flow is pretty low. And a characterized ball valve, which has one example is this kind of interesting kind of double shark fin cut, can fix this issue. So by providing what they call a characteristic disc opening, gives different flows for different open positions of the valve. And there's different cuts you can provide that do different things. The most common one we see in HVAC is called equal percentage, which is that shape I had on the previous slide. So if that valve's fully closed, you get no water flow through it. If you start to crack open that valve, so say about 20% open, that narrow part of the cut really restricts the amount of flow that valve is actually going to let through your control valve. And then as you keep opening, the cut gets wider, starts to allow more water flow, and then finally, once you're almost full open, then it really starts to let the water go through there. So what this does is it really restricts the flow at those low open positions. And so this is just one example of a cut. But here's some other, these aren't pictures of the cuts themselves, but these are what the cuts do. So the equal percentage, that green one, you can see you get low flow as at the start as you open the valve, and then you get more flow as you continue, but you could have the opposite. There's a quick opening one where you start to open and you get all kinds of flow, but then it tapers off on the back end. And then they have these other ones that are somewhere in between. So depending on what you need for your application, you can get different characteristic cuts. Now, the reason we like that equal percentage, where you get low flow at the start and then more flow at the end. So if we were to look at a standard hot water heating coil, what the coil wants to do is this. So as you start to open the valve, at the very beginning, you're going to get a lot of heat transfer, even if your flow is low. That's what the coil wants to do, and that doesn't give you very good control, especially at those low valve open positions. But if we pair that with an equal percentage characteristic, which has kind of a opposite but mirrored effect, what ends up happening is the resultant characteristic of those two things combined is essentially linear. So now when we open that valve 30% open, we'll get about 30% heat transfer. And so by using that equal percentage characteristic, we can get a very good, mostly, I mean, it's not perfect, but mostly linear relationship between the valve open position and the amount of heat transfer we want. So that's ball valves. So next up, we got globe valves. And this is typically used on larger pipe. So I mentioned ball valves are 2 inch and smaller. Globe valves are typically for 2.5 inch and larger. And these operate differently than a ball valve. These control flow by raising and lowering a plug that's inside the valve. So if you have your water coming in on the left, as this plug goes up and down, you can control how the flow is going to go through that valve. The reason we use globe valves in larger pipes is it's more economical. Ball valves get pretty expensive at 2.5 inch and above, but they do make ball valves in those larger sizes. And with the globe valve, they can also have a characteristic shape to achieve different things. So, same terminology as with a characterized ball valve. Fast opening, linear, equal percentage. And so by using those different shaped plugs, we can achieve different things depending on what we want. But again, equal percentage is what we mostly see in HVAC applications. The third type of valve you might see is a butterfly valve. And this is also used typically in larger pipe. And the way this controls flow is by opening and closing a disc, rotating that disc 90 degrees, either fully closed or fully open. Butterfly valves are more economical than both ball valves and globe valves. The problem is they have pretty bad modulating flow control. So these don't have any kind of characteristic cut to them like a ball valve or a globe valve. Once that thing starts to open, you're going to get a lot of flow through that valve. And so usually you're only going to see these butterfly valves if you have a 2-position application where you'll either want all the flow or none of the flow. So that's kind of the basics. I call that control valves 101. Maybe this is 102. This is getting more into the engineering side of things and how we size our control valves. So valve authority. So generally speaking, pressure drop is bad. Normally, we don't like pressure drop because a lot of pressure drop means our pumps have to work harder, our pumps have to be bigger. We need more horsepower, and really waste a lot of energy. So normally pressure drop is bad. Control valves, though, are a little unique in that we do want some pressure drop on these things. Why is that? Reason being, water is always going to take the path of least resistance, which is going to be the path of the least amount of pressure drop. And this goes into this idea or calculation of valve authority, which is defined as the valve pressure drop over the total pressure drop. And I'll have a picture here in a minute to help illustrate this. That valve pressure drop, that's the pressure drop through the control valve only. That total pressure drop is the pressure drop through the coil plus the control valve. And this is always going to be a value from 0, which is terrible control, and 1, which would be great control. We can't ever reach 1.0, but we can at least try to get close. So if we have a coil, 3-way valve, and let's say that control valve has 1 foot of pressure drop. Our coil has 10 feet. So if water was to go through that bypass path and just go through that control valve, it would only have a pressure drop of 1 foot. If we were to go through the coil, which also has to go through the control valve in that same path, that's going to be 10 feet plus 1 foot, or 11 feet for that total coil path. And so if you were to calculate the authority, you have your valve pressure drop over your total pressure drop, 0.09. Not great. Look at the pressure drop through both of those paths, depending on the position of the valve. This is what that would look like. And so you can see the bypass path in blue has a very, very low pressure drop until you get to that, almost all the way to the right-hand side of the graph. And the coil path has a lot more pressure drop through pretty much every other condition along that axis. And so when we're talking about water wanting to go the path of least resistance, it's always going to want to go through that bypass path until that valve is almost completely closed. So that's going to give you very poor control, but it does give you low pressure drop. So if we were to bump that valve up, say put in a 5-foot pressure drop valve, and then we recalculate all these numbers, so now our authority is 0.33. It's quite a bit better. So now our bypass path is starting to come a little more in line, or at least on the same magnitude, at least relatively speaking, to the coil. And so now as you start to close that valve, it's going to do a better job at redirecting that water flow. Still not great. So you do get better control, but we can do better than that. So let's say you bump it up to a 15-foot. Recalculate everything, and now our valve authority is 0.6. So now our curves are starting to approach more of a mirror of each other. And so this is going to give even better control. So as that valve starts to close, you're going to be able to redirect the water through the other path. But you can see our pressure drop through that valve is going up and up and up. And so if you did something crazy, 150-foot pressure drop control valve, don't ever size a valve like that, but let's just say you did. So that's going to give us a valve authority of 0.94. So we're starting to approach this perfect, 1.0 valve authority, which we could never ever achieve. But you can see now you're going to have really good control over that valve. So you got great control, but now you have 150 feet of pressure drop just through that control valve, which that's a whole nother problem. So a flat curve caused by that low authority means you get poor control. So if you can increase that pressure drop through your valve, that gives you better authority, which gives you better control, but higher pressure drop means your pump has to be bigger. So we have to compromise somewhere in the middle. Generally, valve authority of at least 0.5 is good enough, we'll say. So to illustrate that on a graph, if you had a valve with an increasing pressure drop, uh, assumed with an assumed coil of 10 feet ahead. You can see as the pressure drop increases in the valve, your valve authority increases a lot at the beginning, but then it starts to taper off. So let's try to target that 50%, or excuse me, 0.5 valve authority. And I mean, you can keep increasing the pressure drop in the valve, but you start to see diminishing returns. So that 0.5 valve authority valve, that would be a 10 feet ahead pressure drop. If you were to double that, you're only going to get up to 0.65-ish, even though you doubled the pressure drop through the valve. When we're sizing control valves, typically we're sizing for 3 to 5 psi, or 7 to 12 feet ahead of pressure drop at design flow conditions, meaning max flow. So I'd say it's important to check your coil pressure drops against your valve pressure drops, and to calculate your valve authority when you get that control valve submittal. I'm used to control contractors selecting the valves for me, and when I get their submittal, I plop it in a spreadsheet and I weigh that against the coil that those valves are paired with, and I calculate the valve authority. And I use a conditional formatting rule to make sure if any of these values are below 0.5 to flag them in red, which if you aren't using conditional formatting, you're missing out. Similar approach on two-way valves. So real quick, running through a similar graph. So same numbers, but this is for a two-way valve with no bypass. So this would be a 1 foot pressure drop valve, pretty flat curve over the majority of it. If you increase that, curve starts to get a little more steep. And if you just keep going, you're getting more of a slope across more of the curve. And so you're going to get better control by adding pressure drop to that valve. So the flow coefficient, this really kind of piggybacks on the valve authority discussion and how we size control valves. So I said, hey, we size control valves for 3 to 5 psi. But if you pull up a control valve submittal, it doesn't just tell you what the pressure drop is, because the same valve is going to have different pressure drop depending on how much water you're going to move through it. And so they can't give you every scenario and every flow rate through that valve. So if you look at a spec sheet, they're going to give you the list of available flow coefficients, which is abbreviated C sub V. And the idea of a flow coefficient is this allows you a level basis of comparison between different valves, because now you have something to compare one valve to the other based on this C sub V. In equation form, this is what it looks like, with the units being Q is your flow in GPM, SG is the specific gravity of the fluid. That would be 1.0 if it's pure water, but if you had glycol in the system, that would change your specific gravity. The delta P is the pressure drop across the valve in a full open position in PSI. So you might look at that equation and scratch your head and think, well, what the heck do I do with that? That doesn't mean anything to me. But one way it was explained to me that I was kind of stuck was the C sub V value will tell you the flow through that valve, assuming pure water, that will give 1 psi of pressure drop. So if you have a valve with a C sub V of 7, that means 7 GPM will give you 1 psi of pressure drop through that valve. And so if you're looking at a spec sheet, so here's a Belimo valve, two-way characterized ball valve. You can see for that 1/2 inch body size, you have all kinds of C sub V values to work with. So all the way from 0.3 up to 14, which is a pretty big swing. So just because you have a 1/2 inch valve, that doesn't necessarily tell you anything, anything at all. It's all based on that C sub V value. And so when you order this valve, you need to specify, or the controls contractor needs to specify, which C sub V value they're going to use. And these are what's available. So if in an ideal scenario, I wanted a C sub V of 5.5, I can't just go get a 5.5 CV valve. I either have to convince myself, in this case, 4.7 is okay or 7.4 is okay. So generally, higher flow requirements are going to require higher flow coefficients. So back to that rough explanation of what the C sub V means. It's the flow that will give you 1 psi of pressure drop. So if you need higher flow through that valve, you need the higher flow coefficients. What I like to do is to rearrange that equation and solve for the pressure drop based on these known C sub V values. And so this is what that equation looks like. And so if I know what my available C sub V values are, I can plug that into this equation, and I know my flow and I know my specific gravity. Then I can figure out, well, what does a C sub V of 4.8 give me in pressure drop? And now that's something I can actually use to help drive my sizing of that valve. And so really this needs to be part of that valve authority analysis. And if you look back at that table I had a few slides back, one of those columns was the flow coefficient, which I then use to calculate the pressure drop. All right, last up. Looks like I'm right on track. Pressure independent control valves, commonly abbreviated PIC-V. So when we're talking about system pressure, typically measured in PSI, and the flow in gallons per minute through that system, there is an inherent link there. So if you provide more pressure in the system, that's going to want to drive more flow, and vice versa. If you drop the pressure, that's going to drop the flow. The system pressure, even if it's a variable speed system and you're trying to control to a constant pressure, ultimately the pressure at any point in that system is going to be constantly changing, namely because if you have a variable speed pumping system, as that pump speeds up and down, that is going to impact the pressure throughout that entire piping system. And then as valves are opening and closing throughout that system, that's also going to impact the system pressure. So if you have one valve, that's operating, and then the valve 10 feet away from it on the same mezzanine fully closes, that will have an impact on the system pressure in near that control valve. And what that means is that if your valve is 30% open, that can mean any kind of flow depending on what the pressure is. So a big takeaway here is just because you know how percent open that valve is, that does not tell you what the percent flow is. 30% open could mean 30% flow at a certain PSI, but as soon as that PSI increases or decreases, now that goes out the window. And so a PIC-V, it's in the name, pressure independent control valves are able to provide consistent flow even under variable system pressure. The way they do this, the control valve you install has a known flow to pressure drop profile associated with that valve, determined by the manufacturer. And this is going to watch the pressure drop through the valve at any given time. And if you're watching the pressure drop, you know the flow. So essentially, a PIC-V is a two-way control valve and an auto flow and a little bit of software in there, all in one device. So this center one here, you got, again, the Belimo orange that we're all accustomed to seeing. There's two parts here. So this is the actuator part, controlling your two-way control valve. This is the DP part that's measuring what's going on and can actually correlate that to a flow. And so the use of PIC-Vs kind of removes the issue of valve authority, as long as that valve is sized for the correct pressure range. And really, you're going to want to use these anytime you are more worried about getting consistent flow. Normally in HVAC applications, your typical hot and chilled water coils, we're more concerned about delivering BTUs per hour. We want 20,000 BTUs per hour out of that coil. We don't really care as much about how much water flow that actually correlates to. It's all about BTUs per hour for us. So ultimately, a PIC-V is going to give you better control. I mean, I have heard of, I guess what I'd call simple applications like a 4-pipe fan coil or a basic air handler where they've installed PIC-Vs when it was probably a little overkill, and it does give better control, but it is going to cost more upfront. So think about when these might be warranted. Um, it's up to the engineer to make that call. To graphically show kind of how that PIC-V operates, if you have your flow versus your pressure, you can see on the tail end at low pressure and high pressure, you do see a drop and a rise in flow. I mean, basically, you're on the high end, you can brute force your way through this thing and get more flow out of it. But over that pressure range, you're going to get pretty consistent flow. I mean, maybe not 100% flat right there, but it's going to be much more consistent than a traditional control valve. All right, right on time. Does anybody have any questions?